Well, it's so nice to be here and see so many old friends, and I want to congratulate David. I will do it in extended form later, but at the moment it's good enough, I think, to say that we are all very glad that David is here and celebrate his birthday. Well, you see, I thought that there is one method to give either very bad or very good talk. The problem with the method, you a priori you cannot say which one it comes. And the method is not to prepare. The worst you can do is, of course, to use a computer presentation. So I wanted to demonstrate to you that, well, you see, there is one reads often that there are very fundamental problems in physics, like the cosmological constant problem, and which is supposed to be to require some very drastic modification of physics, or even to go beyond physics. Something of the same type usually said about the information paradox. Well, I will try to defend a point of view that by themselves these problems are kind of red herring. Then, in fact, there are real dynamical problems behind, but there is no really fundamental behind these problems. I'll explain what I mean. Let's start with the cosmological constant. Let's start with the Minkowski space first. We know that in Minkowski space we have Poincare group. This Poincare group has representations, fields are representations of the Poincare group, and we built quantum field theory on this basis. These representations are characterized by the mass of particles for a particle with a mass m, and it's basically Wigner's point of view that field theory that particle is an irreducible representation of the symmetry group. And what is remarkable about this representation is that energy is in these representations energy is greater than m, which means that the representation has the lowest weight. Energy is just the weight, one of the weights of this representation, and we have lowest weight representation, which means in turn that the vacuum is stable. The vacuum is stable because if we try to generate a pair of particles, we violate this. It is impossible because of energy conservation. So it is stable, although when as an undergraduate, I remember I was trying to write a paper entitled "Peaceful Uses of Vacuum Energy." It didn't went very far, but now maybe I shall do better. So let's compare it with what we have in the de Sitter space when we have, let's suppose we do have the cosmological constant of a Planck size, and then we try to analyze the vacuum. There is a drastic difference with this, with Minkowski space. The the de Sitter group has no lowest weight. And I shall demonstrate what it means concretely, but it's always already clear from this elementary argument, from the mathematical fact that there is no lowest weight representation. It's already clear that the system is unstable. There is nothing which prevents the vacuum to decay onto particles and to generate particles. Particles will decay to other particles, and it's unstoppable. So there is no chance in such theory to observe a cosmological constant. You will observe something else, and it's difficult. Well, I will try to say something, and it's a difficult question. What will be the end state of such decay? But the fact that there is decay, there is impossibility, that the cosmological constant is impossible, is beyond, it's elementary, and it's very simple. And that's one of the impossible hyperbolae which I had in mind. There's even much simpler case. Yes?
Just the fact that you can create a number of particles,
Yes.
because the universe is static, doesn't forbid the universe of a finite volume of fixed size from remaining considered.
Well, no, I think I will show you that, well, when you either have stability or you don't. And I will tell you a very simple calculation which strengthens this argument. Let's take lambda phi 4 theory and calculate calculate the quantum correction to vacuum energy, which will be given by some diagram like that. That's exactly which I meant by peaceful uses in the Minkowski space. And in Minkowski space is divergent like lambda to the 4 and real, no surprises. If you perform this calculation in the de Sitter space, you again will get divergent and real part of it, but you also will have a finite imaginary part, which tells you unequivocally that the system is unstable. There is
very small, the cosmological term is small, right?
No, I'm not talking about small. The problem is usually formulated like you say that natural size of the cosmological constant is the Planck length. And what I'm saying is that that will explode in your eyes. Then let me look at to make it more clear. Let me tell you even more elementary and simpler case of impossible hyperbola. Let's look at the problem about which thousands of papers have been written, thousands and thousands, I guess, which is accelerated motion of electric charge. So let's consider the Minkowski space this time. And there is a light cone, there is hyperbolic trajectory, and as I said, it has been studied and studied and studied. I will formulate it in my own way, not because of the problem itself, but to make the connection. So if you, in this case, the amplitude for radiating a photon is non-zero, and there's a lot more formula which tells you how the photons are radiated. And there's this light cone serves as the horizon. Namely, although the photon is radiated, there is no way to inform about radiation this guy. What is slightly surprising here, so that's an simplest example of the horizons, and what is slightly surprising here is that if you calculate the force, this friction force, the radiation friction force, it is exactly zero for these things. Actually, there is a very nice formula for all these matters, namely that if we take the amplitude of radiation, which is given by a vertex operator, then where is an eraser here? I think I need an eraser. Oh, thank you. So the number of photons is and total number of photons can be written down in an interesting form. It's a double integral dx dy x minus y plus I epsilon, where epsilon is a time-like vector, and this is almost the contribution to the Wilson loop, and it gives you energy, and you can calculate the emitted momentum. And the formula which arises tells you that you have delta p mu radiation plus delta p mu friction, which in fact is zero, is equal to the certain topological term, which is the change of vector potential along the trajectory. And it explains how it is possible, that's the generalized energy conservation, explains how it is possible to have zero friction and non-zero radiation, and that's the concept. I shall not explain it now, but it's the result of the existence of the horizon. Now, let's consider a slightly modified problem. The only thing I would add here, which is just a digression, that this generalized Wilson loop, this dissipative Wilson loop written here, may be a very interesting object. It's never, as far as I know, never appeared, never been studied. It might be useful for confinement criterion and for many other things, but that's not my direction now in this talk. Just keep in mind that there is an interesting beast which appeared. Now, let's suppose that the situation is like in a black hole, namely there was no horizon in the past and no horizon in the future. Namely, you accelerate charge gradually and you decelerate it gradually. In this case, the horizons disappear. You can see from this formula how this term disappears and the balance still keeps itself, but the real use of this formula, which I unfortunately don't have time to explain, is that in this way you can study the stability of this picture. If you just perturb the hyperbolic trajectory a little bit, what you get is a runaway solution. And that's another version of what happened with the cosmological constant. I claimed that it is unstable. Same thing here happens with the accelerating charge. It's very interesting to study in this case what happens to these runaway solutions when you actually have when the horizon is temporary. There is a question. No usual horizon is permanent, but if you decelerate, it's temporary. Now you will see that very similar phenomena happen in other cases, and we will try now to. There is a yes. No. Well, yes. If you have permanent horizon, then you have runaway solution. That's any small modification, it blows up exponentially. Now let us now look at the information paradox from this point of view, and then I will try to give you the whole picture. Let's consider the de Sitter space prepared in the following way. So let's take and A of t is a constant at -infinity, so something like a function like e to the t tanh. What I'm for when t goes to infinity, it's just the de Sitter space, but as capital T goes, as this t goes to infinity, it is the Minkowski space, and so I have kind of a sandwich. It's a sandwich Minkowski, de Sitter, new Minkowski. So let's discuss the behavior of this sandwich. The reason the reason why it's worth considering is that in Minkowski space we have well-defined notion of particles, fields. We know everything, and so basically you need a safe haven for these de Sitter safe havens, which will show you what went on. It's a little bit like in general relativity. You need you define conserved quantity like momentum, energy through their value in the asymptotically flat space. And let's assume that we have Minkowski vacuum. Then we turn de Sitter, then we turn it off and get excited Minkowski vacuum. We consider a field in this case. And it is very easy calculation to see, very easy to calculate the green function. Here is the standard green function. It goes adiabatically into the so-called Bunch-Davies green function here, and it goes to some excited state here. Field naturally get excited. The interesting thing is that what kind of structure we get for the green function. So the green function, let's consider the green function on this m prime as t goes to infinity. And this green function for the field phi, it has the following structure. There is a thermal green function with the Bunch-Davies, with the Gibbons-Huygens temperature. That's one thing. If it was all, it would be a paradoxical answer, because we started, this green function describes the mixed state, it describes the thermal state, while original green function was referring to pure Minkowski state. However, there is an extra term. This extra term depends on t and t prime, and it contains the terms like t plus t prime multiplied by something. So as t and t prime goes to infinity, this term becomes infinitely oscillating. There is no oscillation here. It becomes infinitely oscillating. As a result, if you have any device with finite precision, this term will become unobservable at infinity. And what you will observe is it will be apparently the passage from the pure state to the thermal state. But that's an illusion. It's just and nothing deep, in fact. Okay, now let's go to so far it's all rather superficial and elementary analysis of these hyperbolic spaces. And you can do it in some other cases, but now let's do something more sophisticated. Namely, let's try to calculate the correction. Oh yeah, I forgot to say. Let me return back here, and there is one important message which I forgot to convey. Namely, this formula is true for the so-called heavy modes of the de Sitter space. Namely, the mode in de Sitter space you have you have the typical square root, like 9/4 of the Hubble constant minus m square. And there are two types of modes. In one mode, m square is greater than 9/4 of h square. In another, it's less. What I said here is that thermal state, quasi-thermal state, is reached if I consider this field phi with heavy mass greater than the Hubble constant. And it's very fascinating and not really, I don't really understand it completely, what happened for the light masses. Suppose now m square is smaller than. If you do the same calculation, there is no problem with it, but you will not get thermal answer. You will get some answer, you will get the green function which behaves like 1 over k to some power, some d divided to some power alpha. I will not specify it. It's not thermal. So it seems nature. I'm not sure that what I'm saying is right. Well, this is the calculation is right. There is no question. But the interpretation I am a bit uncertain about. Namely, it could be that you produce that there is in the Sitter space there are heavy modes which live at Gibbons-Hawking temperature together with the light modes which are not thermalized at all. What? Yeah, but it's usually if you that's because your detector in Gibbons-Hawking is actually always semi-classical, and it's always a heavy mode. So there's no. What? That's right, but at the same time, the physical field, when you calculate the physical field, you will get for the light mode. It doesn't depend on which patch you are on. It depends on how you define the temperature. Okay. Yes. Oh no, there is a Sitter invariant. It's fine. There's this. It's of course. It's not. I'm not considering massless modes. massless modes would be slightly messy. But light modes are okay. It's just the so-called, from the representation point of view, it's a complementary representation of the de Sitter symmetry. So there is a question here. Maybe I have a wrong interpretation. I don't know. Now, and by the way, since Indy asked the question, it reminded me, I forgot to mention one more interesting feature here, namely the photons emitted here in this case, they have, as all photons, they satisfy the Lorentz condition, from which it follows that for k non-equal 0, you have two polarizations as usual. However, when perpendicular momentum is 0, there is something which reminds me of well, what happens is that this constraint disappears and you have 3 degrees of freedom, which reminds me about work done in the 60s by Zildovich and Sinyaev, who discussed Bose condensation of photons. So that's one interesting comment to be kept in mind, again undeveloped, that perhaps there is some analogy between radiation of accelerated charge and the Bose condensation of photons of Zildovich and Sinyaev. But okay, let's leave it at that. Now, how much time do I have? 10 minutes. Okay. Now let's, as I said, let's start considering more sophisticated things. This is all elementary and in some form you probably know. When we try to calculate, we have a choice at first, it seems, whether to work in the flat space, whether to work in the full de Sitter space or to work in the Poincare patch. So if we define n plus n minus n as a unit vector, define it like that, we have this is the de Sitter space, and there is a very convenient and seducing parametrization by Poincare, which covers only n plus greater than 0. And the all work in inflation, etc., inflationary models, they worked in this incomplete space. What I will try to say now is that, first of all, working in incomplete space is not a good idea, because it violates unitarity. Particle go away. But if you do, even if you do work in this incomplete space, there is some non-perturbative instability which must be taken care of. There is again instability of the type we discussed before. And the third thing, which I will try to explain this. There is a runaway solutions in these cases. So let me also draw the Penrose diagram. The future infinity is here, past infinity is here, and we have the light cone, which if you are inside the light cone, that's the Poincare patch. If you calculate the correlation function here and calculate the correlation function, for example, we take phi square and start calculating, we have to deal with a diagram like that, and we have to put pluses and Keldash's pluses and minuses here. This is if you take momentum Q. It's actually, it's not a difficult calculation, and it shows that, so there's a kind of a, you also have to, when you do calculations, you have to supply some arrows here. And my name for this diagram is slings and arrows. And well, it's not exactly mine, it's Shakespeare's. So when we calculate it, we get no divergences in the Poincare, on the Poincare patch, which is a good news at first, as it seems at first. No divergences in this order. However, when you consider, that means simply that the correlation function phi, normal correlation function goes like e to the minus IML, and L is the geodesic distance between 2 points. We get an extra factor e to the minus gamma L. And it turns out when you that because of the instability I mentioned, because of instability of the de Sitter vacuum I have mentioned, all correlation functions will be exponentially damping. Let me explain what I'm trying to say. You see, when you have Fermi liquid, for example, we take a quasi-particle. It contains, its energy contains an imaginary part. And particle near Fermi surface decays and so on. However, there is always excitations. It's not a permanent decay. We know that Fermi liquid settles down. If you add a particle, it will settle down to some stationary state. So there are correlators which will never be going to zero exponentially. Here we have something more similar to what in dynamical system theory is called mixing. Namely, all correlation functions decay. It could be actually this, there could be subtleties which have not been analyzed so far of the type of Larkin-Ovchinnikov mechanism, but I will not discuss them because I don't have much to say about them. Okay, now comes the very crucial point that in this approximation, next correction is not of Bunch-Davies type. It contains it is more similar. It's hard to explain. There are explicit formulas for that. It contains the pieces which are not Bunch-Davies, which look more like alpha vacuum, and when they are substituted back, they will lead to instability. They lead to runaway solution, even here. So in this case, you have to go first to this order. There is no runaways, but in the next order it appears because of this mechanism. So that's one message. And another message, let's do the calculation in the global coordinates, in the full space. And there is an interesting feature here. You see, it's a bit, the calculation simplifies drastically and also shows some new philosophical meaning. If you notice the following, that calculation in the global universe are for certain quantities is equivalent to the calculation in contracting universe. I shall explain this. That's important. So there is what I'm going to say is that there is kind of duality between expansion and contraction. EC duality between expansion and contraction. What I have in mind, look at the Penrose diagram. Suppose we want to calculate the phi square function somewhere here. When we calculate it in causal way, we have to we understand that it is influenced by interaction in the past light column only. Okay, but consider all these interactions. Let me draw it again. It's getting messy. Now it's getting even more messy. So we have the past cone of this guy, and it lies within this cone. This cone, as you see, it's a horizons which define contracting universe. This is past, the universe was big, and it contracts to the point. So you see that the causal calculation of the phi square is the same as calculation in anti-Poincare patch. So instead of being instead of working in Poincare patch, one should be working in anti-Poincare patch, and that will describe the global universe. That simplifies drastically the calculation, and you immediately demonstrate that you get secular term in that the phi square gets a secular term, terms proportional to the absolute time, which is the time from the turning on the interaction to the moment of observation, 2 minutes. Okay, there are a couple of more things which I wanted to say. So that has not been analyzed, and we don't know yet what it will lead to. I will maybe I already gave you the spirit of this type of calculations. There are plenty of things which should have been done and haven't been done so far. What I will tell you, what else I will tell you, they will definitely will lead to runaway and destruction of the cosmological constant. I will give you one more idea. First of all, when we look at all theories of inflation, they disregard this effect. I believe it means that although inflation itself as kinematics is well, it's a great idea and very likely correct idea, all the models of inflation I think are wrong, because they disregard important effects. The real mechanism of inflation is different. It must be related to these quantum effects, and as one possibility I will give you an idea which I discussed with Victor Ihot, and the idea is the following. In order to get large-scale universe from the Planck size, the well-known way is inflation. But maybe there is another way. I'm not. We need the inverse cascade, the cascade in turbulence. The direct cascade in turbulence is the following. You have a big fan which creates very small momenta k, and then very large eddies, and then they start to cascade according to Kolmogorov. That's clearly not what we want. We want the creation of big universe. We want the inverse cascade. The inverse cascades are well known in two-dimensional turbulence, and they are not well known, but they exist in the certain type of turbulence which was discussed by Zakharov and Yehot. And in this case, you have turbulence of the so-called Clebsch coefficients, which leads to this inverse cascade, and that might be looked as an alternative to zero. Do you have negatives? Or maybe periodic numbers? Okay. It looks like 7 as the default. Well, okay, let me summarize. My point is that there's we learned a lot about quantum field theory. We developed intuition about quantum field theory, mostly in the Minkowski space. It is a completely new game to discuss these things in the curved de Sitter universe. The size of the symmetry group is the same as the Poincare group and de Sitter group, but quantum field theory is very different, and it will take quite some time, I guess, to get used to it. Still, field theory is such a wonderful subject, which is provided us with new toys, and it's quite clear that we will have our we will have problems for the how shall I put it, the a number of problems which are solvable and which are interesting and which will influence our view of the universe is huge, and we just scratch the surface of it. Let me stop here. Yes.
What are you actually imagining?
Eventually, I hope yes. Yeah, but in Minkowski, you have this. You have stability. You have mass. Well, that's hard questions, and you see, I'm just the time. So all we have for the time scale is, well, you see, you can imagine that the time scale that after initial dynamics defined by the Planck time scale, you will get some self-similar solutions for the universe, and then you will have some anomalous dimensions which define time development and so on. But it's all fantasies. It's your question goes far beyond what I know, and I'm just trying. You see, it's just. At the moment, for me, it's just piecemeal thing, which I'm trying this and that to collect, to develop the intuition. There's no pretense that it's anything like realistic models. It's just phenomena, just mechanisms.
What signal would
Okay, I'll try something speculative now. But for instance, when I draw this picture, maybe it's too crazy to be discussed with time reversal. Well, what I said that this is the expanding universe. This is the expanding universe, and why we get different results when we look at the global case, because there are pairs or particles created behind the horizon which cross the horizon. And what you observe is effectively the propagator which which is very different from the Bunch-Davis one, and these propagators generate runaway solutions. Now, the totally crazy thing to think about this. So you have particles coming from afar, crossing the horizon, and then influencing you here. A totally irresponsible thing to say would be to say to relate it to the origin of the cosmic rays. That that's one of the signals. Probably I should have said that.
Last good question from each one.
Very quick question. I understand that what you are saying with cosmological term, it is subject to some kind of a self-adjustment
Yes.
mechanism like axiom, right?
Yes, right.
Whenever you put it in the beginning, it relaxes to zero.
Yes.
I didn't understand your argument. What is the outcome of your consideration of information loss paradox? Is it there or it
Oh, no paradox, trivial thing. Just it's just you have or trivial thing, or the fact of life, if you want to put it this way, which is the same thing. But when you have finite, you have to coarse grain. That's the only message is that without coarse graining, pure state go to pure state. With coarse graining performed by your measuring device, they just go to the thermal state. So it's very unexciting answer,
you
I would
have
say.
to measure very precisely? Right?
Yeah, but the more precise you measure, the more, well, it's a usual story starting with, I think, such arguments have been done in 19th century, so.
Okay, thanks again. And those of you who want to go to the tour, just sign up during the lunch break. And lunch will be at the Belgian House.